This
So
conference will now be recorded.
sorry for the wait, which was nothing in my hands. Okay, so let's start our discussion on uh, extended Kalman filter. So before going that one, I will again explain you what is this extended Kalman filter, and then I will take it forward. Okay. So first of all, I will explain you what is the what is the normal Kalman filter, and then I will continue for the extended Kalman filter. As far as if you see here, consider the discrete system. This is the discrete system or the discretized version of the linear system. Whereas in the linear system, you can see x dot equal to ax plus bu and so on. So the discretized one I have written as xk equal to fk minus 1. This f is I have represented for the discrete systems, whereas the equivalent one is the a. This G I have represent, which is equivalent to the B, and this WK minus 1. So this WK minus 1 is something which you are not aware of. This WK minus 1 is the noise, or you might have heard about the disturbance. So there is a quite difference between the disturbance and the noise, although both are affecting the plant in certain way. In general, the disturbances are slow varying signal, whereas the noise is the fast varying signal. And this particular parameter which is affecting the system, we assume as Gaussian for the derivation of the Kalman filter. And this is the output equation, very much similar to y equal to cx. In the discrete, we have written zk that equal to hk into xk plus v. And these are the noise terms. So this noise, the covariance is the normal distribution with zero mean, and qk minus 1 is the covariance of this particular noise. That means if this Q is very large in a very colloquial language, if the Q is very large, then I can say that yes, the noise is very high. And this Vk is the one which is called as the measurement noise, and the corresponding covariance for the measurement noise is Rk. So, so now what we are going to do here is we will see how to what is this Kalman filter and how to simulate or how to derive a particular Kalman filter, a particular system. So the first thing what you have to assume here this Kalman filter in its naive form is only for the linear system. When the nonlinearity comes into the picture, then this will become the nonlinear or the nonlinear version of the Kalman filter, and it is called as an extended Kalman filter. So now I will just explain you, and this is the way to discretize the system. So Euler's method is one such method. This is my A is my continuous plant, and AD is the discrete plant which is equivalent to the F, then I plus A into dt, where dt is the sampling time. And similarly B into dt. So this dt is the sampling time, if B is continuous one, then B underscore D is the discrete plant. So why we have to go for the discrete? Because most of the nowadays almost all controllers are discrete in nature. So that's why this A underscore D and B underscore. So most of the Kalman filters are implemented in the discrete ways. So now what I'm going to do here is I will be explaining you some aspects of Kalman filters, and then I will see what to how to proceed further. So basically, the Kalman filter has two stages. One is called as a prediction, and the second one is called as the update. I will show you what is prediction and what is update. Just give me a minute. I will show you. I will try to derive the things. Shiva, flip just. നല്ലതല്ലേ എൻ്റെ കേൾക്കുന്നില്ല. Yeah, that's fine. Let me derive is visible.
Hello, hello, sir. Sir, not visible, sir, and also not audible.
Sir, sorry, is not this. It's some connection issues. Let's start our discussion on this one. Consider the discrete system given by like this. So there is a, this is the noise, and this WK is the process noise, as this and the measurement noise. So now what we'll do here, derive or we'll try to see what are the different things. So the first thing is we have to discretize the continuous system, and once this discretizations happens, then we have to go for the discrete Kalman filter design. So this is the big algorithm, the Kalman filter algorithm. However, I will try to just split this into a very small set of 5 which I want to show you. That is the purpose what I was trying to do. So I will be trying to explain you these things now. So there is only 5 ways. So can you able to see something? Yes,
Yes,
sir.
sir, we can see it, sir.
Yeah, am I audible? Okay, fine. Now I
Sir,
will try to derive the equations. It will be quite for a minute. It will take only 5 minutes. I will explain here. So let us assume the discrete system is given by xk into or xk plus 1.
Hello, sir.
Yeah, hello.
Yes, sir. Sorry, sir. Sorry to interrupt you, but the voice is not at all clear, sir. Like it is completely breaking, and even the video is not clear. It is a blur. Like
Hello.
I think some delay is there. It is not visible.
it is not visible and even
Is
not.
it better now?
No, sir.
Okay. So I think I don't know today why it is happening like.
Now okay, sir. Now it seems okay.
Sorry. Hello. Audible?
yes, sir.
Okay. Okay. So let me continue. I will not write. It's as soon as I started writing this something, so it is not working. So let me. Right. Okay. So all of you, please be mute. So I think now it is better. So let me start my screen now. I'm sharing the screen. I will explain you each of the things what is happening there. Am I audible now? Could anyone please respond?
Yes, sir.
Yes,
Yes.
sir.
Yes, sir. Yes.
Okay. Okay. Thank you very much. So the Kalman filter, as far as the Kalman filter is concerned, there are two different things. The first thing here is the prediction stage, and the second thing here is the measurement stage. As far as the prediction stage are concerned, we try to predict the state estimate as well as the covariance estimate. And once the measurements comes into the picture, we update the predicted value along with the Kalman gain. So before going into much details of the Kalman filter, so let me explain you what is the Kalman filter. The Kalman filter is an optimal state estimator. The Kalman filter is an optimal state estimator. That means it tries to minimize some kind of optimal optimization function to such that the error between the actual state and the estimated state is zero. The similar thing what we have seen in the earlier classes, whether it is the Leuenberger observer or whether it is uh, the sliding mode observer, the purpose was the same. So we try to estimate the states, whereas in the advanced versions we try to estimate the faults as well. So one can use the same thing for the parametric estimation as well. So the Kalman filter has its own advantages. So why this Kalman filter was proposed? It was proposed in 1960s. The problem was with the Wiener filter. Long time back, the NASA was using the Wiener filter because it is a frequency domain approach, and it was very difficult to apply or implement if for the non-stationary signals. So then Kalman has proposed a single four equations for the state estimation. Uh, just to inform you that the Kalman filter has sent this Kalman filter work to the IEEE journal, and it was outright rejected. And then he submitted this paper to some obscure journal, I think some ASME journal of in general engineering. And from then, I think Kalman hasn't published in IEEE. So, but this Kalman filter is the workhorse for almost all industries. It doesn't matter where, all industries people uses this Kalman filter. So to start our discussion with Kalman filter is a two-stage process where one stage deals with the prediction value. So here, so in general, what we do here is we try to predict the system response, and from the predicted value, once the measurements comes to us, then we update, and we call it as the updated state or updated covariance. So the two stages what you are looking there is the prediction stage and the measurement state, and it is a recursive method. That means for each time step, it keep on repeating the prediction stage and the measurement stage. So in general, what we do here is we try to predict something first, assuming that there is no measurement available. And once the measurement is available, then we update the predicted one. So the concept here is how do you predict? The concept here is how do you predict the state? If your prediction is very good, you don't need in general the update. If your prediction is very weak, then you need the concept of update. So when can you say that it is it is good or bad? That depends upon the error. And how do you find the error is a big question. And in some cases, you find the error just by subtracting the states with the corresponding estimates. And in our particular case, in this particular case, we are trying to predict the error based upon some sensor measurements. So it is not exactly the complete state what I can say that state error. So our aim is to minimize the state error, state estimation error, but it is completely depends upon the output. So how one has to do the state, or how one has to minimize the state estimation error based upon the output is the big task. To start with, we will start our discussion here. You can see this xk plus xk at k minus 1 equal to f of k into x minus k minus 1. So to start this Kalman filter, the first thing is you need this initial variable, you need the initial condition of the plant as well as initial condition of the covariance. That means you should be knowing what is the initial state. Suppose in most of the cases, the initial state of a particular plant is zero, but in some cases, energy is stored. The
Hello,
initial
sir.
state energy. Yeah, hello.
Sir, your voice is not audible, sir. I think some disturbance or something is
Some
wrong.
disturbance is coming. I'm sorry, what is happening? I don't know today. Is it better now?
Yes, sir. Yes, sir. It is better now.
Now it is
Okay,
better.
okay. Okay. So this is the initial state vector which one always required this one. And once if we have this initial state vector and the initial covariance, then we have to start the prediction. So all of you please see what is happening here is first of all we'll set k equal to 1. If I set k equal to 1, then what will happen here? X hat of 0 at 0. Okay, and I assume that u is available from some way. And similarly, if I set k equal to 1, this will become p0 at 0. Since this initial condition is available, or we assume that we know the initial condition, then we substitute that initial condition here. And similarly, if this initial condition is known to us, since you know fk minus 1, this is the control part. You assume that control and estimation are the separate one. This is coming from the control area, so control part, so you can leave this one. So this fk minus 1 is known. This is a plant matrix. So this now when k equal to 1, this will become x0 at 0. So x0 at 0 is known to us. Similarly, to find this predicted covariance, this is k at k minus 1. That means we are trying to predict the value at t equal to at k value based upon the previous k minus 1. So how we are doing this? This plant is known. So the first thing here is f p of 0 at 0. So p of 0 at 0 is also known to us. Plus qk. This qk is the noise covariance, which is also should be known to us. So what are the, apart from these initial values, apart from the initial value of the states and the covariance, you should be aware of the q and r. So the Q and R are basically the process noise and measurement noise. So now, since for this, based upon these initial values, when k equal to 1, you know what is this. So then, once the measurement comes into the picture, this is the measurement. So this is similar to the Y. Then what we do here is the measurement. So updated. So we call it as updated. Updated state has this predicted value plus some gain values. So this predicted value, since I have this information here, I will copy this information and I will paste it here. So I will bring this information from to here. And these are the things which are not known to us. So what is this KK? This KK is called as the Kalman gain. How do you evaluate the KK is given in this particular equation. If you see this KK, it consists of PK minus 1, predicted covariance. So prediction, whenever you say the K at K minus 1, it is coming from this step. So this is already known to us. So we'll directly substitute here. This H is plant parameter, which is equivalent to the C matrix, which is also known to us. So this becomes HP H transpose plus R. So this R is also known to us. So this is, and again the inverse of this one. So in Kalman filter framework, this HPH plus R is called as innovation covariance matrix. So this matrix is the innovation covariance matrix, and inverse of it should exist. In the what will happen is inverse will not exist if the determinant of this particular matrix is 0 or so on. So practically, what you can say that practically there is some Kalman gain, sorry, this noise, there is some noise in the system, then you can estimate this very accurately. If this R becomes 0, let us assume if this R becomes 0, then what is going to happen? If this R becomes 0 and if you take the inverse, then some of the terms will get cancelled. So this HT and this HT inverse will get cancelled and this PK and PK inverse will get cancelled. Then your Kalman gain is nothing but the output matrix. So it will not work. So to make the Kalman filter work dynamically, this is very important, dynamically, this R, there should be some R value. And basically this R value, you cannot assume that always, always the measurement noise is 0. Whatever you do, there will be some measurement noise from the sensors. It could be of the order of, micro or nano level, but it is almost impossible to get the accurate measurement from the system. So once this step is over, this Kalman filter you calculate and you can substitute the Kalman filter here. So next thing is what is required here is this VK. So this VK is nothing but ZK. This ZK for whatever we are getting here. And ZK is we are getting as the output, and this H is already known to us, and this XK minus 1 is coming from this prediction. So now the complete information is available with us. I will explain one more time when k equal to 0 for when k equal to 1, what is going to be the first time step in the discrete one when k equal to 1. So this is known to us, x0 at 0, p0 at 0 is known to us, q and r is known to us. And apart from this, you should be knowing the f, which is the plant matrix, and g matrix. How do you calculate this one? This is called as a predicted state. The predicted state, you can calculate the thing which is required for this one is x0 at 0 when I substitute k equal to 1. X0 at 0 is the initial condition. I will substitute this control is not required, is no. For this one, P0 at 0, P0 at 0 from the initial condition substitute here. And this KQ is called as the noise covariance, which is known to us. Once this measurement is available from the sensors, that means ZK is available, then I will update my predicted value and then I will check what is happening. If you see XK at K, this is XK at K, that means 1 at 1. So now here already it has been evaluated, this Kalman and VK, and this Kalman gain you can get something like this. So this is the equation. For to calculate Kalman gain, you need to have this PK at K minus 1. From where you PK at K minus 1 will getting, you will, this is already known, so it will come from here. And H transpose is also known to us. So again this PK at 1. So this R is also known. So you can able to calculate Kalman gain. This is called as a Kalman gain, and this Kalman gain you substitute here. And this PK is generally it is called as a residual. Residual means it is the actual measurement means minus estimated measurement. So what this K, HK is the plant parameter known to us. This XK at K minus 1, it is coming.
Sir,
KQ
what
is
is
coming from
RK,
here.
sir? How we know?
RK is the noise covariance, madam. RK is the noise covariance. So generally, for the manufacturer will give you this RK value. So
Okay, sir.
manufacturer
Thank you.
will tell you your how your sensor is. If your sensor is very noisy, the RK value will be very large. Okay, so once this is happening, so what at the end of this thing, what you're getting x1 at 1. So the next stage we have to substitute. It will go back here. That means when you proceed to the next time step, that means when k equal to 2, then what you will be doing when k equal to 2, then again the procedure will start. For k equal to 2 at 2, if you substitute k equal to 2, then what you are going to happen, this will become k1 at 1. And from where we are getting this k1 at 1, in the previous iteration we discussed how did we get the k1 minus 1. So whatever the values we have state and covariance we have obtained in the previous case, the same we will be substituting in the next iteration. So it is a kind of recursive iteration. That means it will take the information from the previous state, and it is a kind of Markov. Markov means nothing more than that. In a very simple way, the current state will have all the information of the previous state history. That means if I say that x2, so let us assume x10. That means x10 will have the information about all x1, x2, x3 up to x9. So you don't have to go for the x1 to x9. You don't have to keep that information saved. So that is the very good advantage of this Kalman filter. Only the recent past, the previous step is enough. Previous step value is enough to calculate the future one. Unlike in some cases like moving average filter also, where you have to keep on moving a set of time dependent states up to certain level. So that is not there. So this process will keep continuing. So this is important. If anyone having clarification required in this one, please let me know, because this is very much important. I know it is a bit difficult to digest, but in case if you have some difficulty in this one, otherwise I will be going to the next one. So,
Sir, this is Ravi Kiran.
Yeah, Ravi.
Sir, RK will be generally given, we can get from the sensor data, no, sir? But
yeah, from the
manufacturer,
since manufacturer they will give, yeah.
But what if
However,
the parameter will change with time? Will it affect KK
you have
performance
to.
of the?
Yeah, definitely. This RK is just the first such value what your sensor manufacturer will give. But in practical, if you use the very low value of RK, then your simulation will look like, but there will be mismatch between your actual sensor data and your simulation. Simulation, you can assume that RK is very small. All results are very fine. But if your sensor is highly noisy, then you have to use this RK value as very large. So that is what the trick here is. Sensor
We can update it.
manufacturer may give you some RK, you cannot use it unless if it is very expensive and very accurate sensors, then you can rely on them. But still there is some tolerance there. Still there will be some error whatever they give. So try. So for realistic, for the simulation, for the papers, if you choose RK very small, the results will look very fine. But in the realistic situation, it's not. You have to ensure that you are whatever the RK you're giving, it should sensor noise. Just for the sake of something, you cannot take the smaller. If you're taking some small value, it will work fine in the simulations or in the simple case, but it will fail in the real life application.
If we take too big,
Okay.
like if in, let us say, in hundreds, so what will happen
Yeah.
to the performance of
It will be very noise. For example, if your state is 1, and if you're saying taking the R as 100, that means instead of 1, your value will be plus 100, 100 to minus 100. It will keep on varying that one because it is a zero mean noise.
yes.
Suppose if your speed is, let us assume 10 RPM, and if your sensor noise you are assuming it as 100, so even the speed is 10, because of the sensor noise you are taken too large, it will show you the error something oscillating between 100, 110 to minus 100 or something like that, plus 100 to minus 100 or so on.
In that case, how do we decide the value of RK? Like, we have to completely know about our sensors, no?
Of course, you should have the good information about your sensors. If you don't know you should not be too optimistic, and you should not be too pessimistic. So you have to rely on sensors. Some reliable sensors. That's why the concept of estimation has come into the picture. If you know that some sensors are quite reliable, then go for one, and unreliable sensors you can estimate by using the estimator. So that is the actual philosophy behind this data estimation. So reject the sensors which are very noisy and which are unreliable, and use the sensors which are quite reliable, and rely the data based upon the reliable sensor and do the estimation of the unreliable one.
Okay, then we have to add this Kalman filter to some other algorithms. Like, how do we reject a noisy sensor or something like that?
Yeah,
Correct?
yesterday I told the fault detection. I told, right? If you're using the redundant sensor, suppose even if you use the 3 sensors from the same manufacturer of the same quality, one sensor can be the faulty and the another 2 sensors can be the working fine. Suppose if you are using the triple redundant sensor, that means to measure one particular value, let us assume you are using the speed measurement. In general, people uses triple redundant sensors for the real life, applications. That means 3 sensors you will be taking the same single output, but 3 sensors. You are using 3 sensors to measure the single, let us assume, one speed of a DC motor. 3 sensors. Then you have to use some logical fault detection and fault isolation as well. So you have to see if all of them are giving almost the same values, then you can take the average of that one, and that is fine. If one of them is is giving some weird value as compared to other two, you have to isolate that particular sensor. That is called as a fault detection and isolation. So if the sensor is very is giving some random values, whereas the other 2 sensors are giving the within a reasonable tolerance value, then you should isolate that particular sensor which is giving the nonsense value. So that is called as the fault detection and isolation, which I have not discussed. The isolation, there are various isolation mechanisms are there, so which I have not discussed. I have told only detection and how to find whether there is a fault. If the fault is in the sensor, then you can isolate that one. That is called as FDI. Okay.
Thank you.
So let's go to the next slide. And this is for the extended Kalman filter. The concept of normal filter or the extended Kalman filter, everything is the same. However, there are some differences. What is the difference? And when this extended Kalman filter will fail, and that we will discuss. So this, whatever you're seeing is fk minus 1 into uk. This f and h are the nonlinear functions. Yesterday we have seen what is nonlinearity, like x square, x cube, or sine term and other things. So generally all real world systems are by default, it is due to the inherent nature of this nonlinear. But we sometimes we approximate and we say that yes, the nonlinearity is very small, so we try to approximate with the linear thing. How do you approximate with the linear? So the idea here is, if this is a nonlinear one, and nonlinear equations can be expanded by using the Taylor series approximation. LS approximation is the one where you can expand this linear into Jacobian, Hessian, and higher order terms. So when it comes to the state estimation, we preserve only the Jacobian terms, and the higher order terms, we assume that they are zero and they're not considered. And the Jacobian of this particular matrix, a particular nonlinear system, we represent with as delta fx. So this is the Jacobian. And similarly, this h is also nonlinear. If you take the Jacobian, Jacobian is nothing but partial derivative of the particular nonlinear equation with respect to the x, dou h by dou x, and so on. So if for this dou f by dou x is this is my partial derivative of this f with respect to x, if I substitute at the particular operating point, we call it as a Jacobian. And this is again the same thing. Everything is the same. Only what you can see that earlier here there were some linear terms we were using, but since it is the non-linear one, we can directly use this nonlinear equation. However, you cannot use the nonlinear equation because this p is the matrix. This p is the square matrix of equal to the size of the A matrix or the F matrix. So you cannot simply multiply. You cannot take this one and you can multiply and do it. So that's why there is the requirement to have the Jacobian matrix. The Jacobian matrix is nothing but partial derivative of this one. If you take the partial derivative, this is one. The transpose is this one plus q. Everything is the same. And in the update, all the formulas will remain the same. The only thing here is you can see that for the covariance calculations, this you have to use the Jacobian of the particular uh, H as well. Whereas only for, you can see from here that only for the covariance calculations, you need to have the Jacobian values. Otherwise, you can directly take the nonlinear values here. Why here again Jacobian is because this K is a matrix, identity is a matrix. You cannot just simply, multiply the matrix with the vector provided. And again, just for, to set these dimensions and other things, you need, and this is a big derivative, right? And so this is why we need this one. So remaining all are the same thing. So now this is the extended Kalman filter. We need, the initial state, initial covariance. We set k equal to 1. The similar thing for to calculate this one, we need x hat 0 at 0 from here, and for this one p0 at 0 from the initial condition it is coming when k equal to 1. And here this xk at k minus 1 you will bring from it here, and you need to have the k calculation. K will be coming from here where h is no, and this is the predicted one. Predicted will come from here, and h transpose plus r whole inverse. And in this way you are able to calculate the gains, and hence this gain can be substituted here, and this will give us the complete analysis. So, and in the next step, whatever you are getting this, whatever getting you xk at k x1 at 1 or p1 at 1, when k equal to 2, then these values need to be used as the initial condition for the respective prediction and the measurement update. So that is the same thing. So now I know it is a bit difficult, but just I'm giving the glance of these things, and I will give the simulation as well, which will make your life a bit easy. So this is the plant, which I have considered a simple DC motor plant, which we have already seen. And this is the estimator. So the Kalman filter estimator. So what is happening? This is a nonlinear plant. So measurement is going, only the measurement is going here. I will try to zoom if I can. No, I cannot able to zoom. Okay, let me zoom in this way. If you see this one, the measurement, so current is the measurement which is going from the plant by using some current sensor. And the control input is separate. I assume that this is the PID controller. And this Q matrix is going something here. R matrix is going something there. DT, and some initial conditions I given it as 0, and the load torque is also going. And then I am estimating this all that both the states based upon only this measurement. And then the estimated one, then the estimated speed, whatever the estimation has been done, that I have given for the speed. I assume that speed sensors are not there, but my desired specification is that my speed error should go to 0. That means I should have a speed sensor, but I don't have the speed sensor. Only I have the current sensor. So based upon the current sensor, I estimated the speed value, and the same reference, whatever it is going to the closed loop plant, and the same reference I have given. And I would like to see how the results look like. Before going to that one, I will explain you the EKF code. So this EKF code, this is my nonlinear plant. So what I'm going to do here is, I'm trying to calculate the Jacobian from this particular plant. And this Jacobian is given by, this particular matrix. So which already you know how to calculate the Jacobian, because we have already discussed in the very first class how to calculate the Jacobian. So the plant is nonlinear and this is the Jacobian matrix. So what I'm trying to do here is I'm trying to do the prediction value. So this is the Jacobian one, and this what I'm trying to use here is pk. The pk is fp into fk hat plus q. So that is what it is happening, and plus q, the q, whatever the q is here, it is coming. So this is Jacobian matrix. So this particular all calculation is for pk at k minus 1, and this will give us I plus 80 what we have seen. So this is basically the Jacobian one, and this is the measurement, which is the my first state, and residual, that mu value what I am showing is measurement minus z hat. So measurement is the one from the sensor and z hat is what we are estimating, and h equal to 1 0, since the first state only I am trying to I am assuming that is available. And this is my innovation thing, the same thing, s equal to hp h transpose, again p h transpose. So here you can see that my measurement is linear whereas my plant is non-linear. So that's why this, whatever this delta h and this h are the same here. pH by s. Why this pH by s? Because if you see this calculations, whatever here it is happening. So you can see that pH transpose is this one, pH transpose into this s. S already we have seen. S is the innovation, we call it as, which is HP H transpose plus R. By S means, that means this is S inverse. This is becoming S inverse, where S is this one, and the same thing, this is inverse. And the updated one, P equal to I minus KH into P. So the I minus KH into P is the updated one. Then H hat out, this means the next, for the next iteration, this is the H hat. And it will keep on, prediction and update. It will keep on rotating. So now I will show you how the results will look like.
Sir, I have a doubt. Can I interrupt?
Yeah. Yes.
So, what if there is a propagation delays, like there will be some computational time, na sir, like to estimate the
Yeah.
speed. So there will be some
Yeah.
propagation delays. So how do you
Yes.
cope with
Yeah.
those propagation delays?
In general, by default, the Kalman filter has some tendency to deal with the sensor dynamics, because the sensor
Okay.
has, in general, the sensor is the first order. You can approximate the sensor with the first order, or in some cases up to the second order. And the sensor dynamics, if you consider the Moog actuators or Moog sensors, they have the frequency of around 100 hertz. That means in 1 second they can give you 100 samples of data. And in its naive form, this Kalman filter can deal with that. In case if the time delay is very large, and if your sensor couldn't, if the sensor is very slow sensor, if the time delay is very large, then the extension of this particular extended Kalman filter are called as a time delayed extended Kalman filter. You have to consider the time delay in the derivation, and that is called as a time delayed extended Kalman filter, which is beyond the scope of this work. So that time delayed extended Kalman filter, you can pre-calculate up to what value based upon certain theorems, some numerical theorems. You can pre-calculate that based upon the system and the sensor dynamics up to what level of delay. So you can come up with some which say that okay, if the delay is 1 millisecond, then it will give the stable state estimate. So that is called as a time delayed extended Kalman filter or time delayed Kalman filter, which is also available in the control literature. So you can go for this. Is in its very naive form. We assume that the sampling data of from a particular sensor is 100 hertz in most of the cases. Minimum is 100 hertz. Maximum it can be go to very large values as well. So 100 hertz, and 100 hertz in general it works very fine. So that is
Okay.
my answer.
Thank you, sir.
So now what? Yeah. Now what I will do here is I will show you this small piece of simulation, and I will show you this is the plant, this is the actual plant, and this is based upon estimated plant. And if I run this one, whatever I have seen, the code is the same thing. And this is in my plant, this is the reference and the actual plant tracking. You can see how it is happening in the full state feedback. That means I assume that the sensor is also available. If the sensor for speed is also available, if it is not available, if I am using only the current information like this, what I'm seeing here, and if I use the estimation, and then what I'm going to see is I'm going to this is from the plant and this is from the estimator. I'm going to see, I'm going to compare what is happening, and this is actually the error, the absolute value of the error. You can see that error is going up to 0.35, whereas my input here is 30. So 30 and 0.5 by 30 is approximately, if I say if into 3, almost 1.5% error. So this is the absolute error value. You can see that what is happening. And if I see, so 1.5 error is okay. And this is a speed comparison. What I'm going to do is I'm trying to estimate the speed from the estimator as well as the plant. So you can see that it works, it is working very fine. However, if I particularly zoom this one, the whatever the error we have seen, system is very slow now. You can see that the amount of whatever 0 point, whatever the values you have seen, that corresponding values you can see here. So you can see that, and this whatever discrete thing you're seeing, this is because of the discretized version. If you wanted to make much smoother, then you have to change the DT value as very low, and you cannot choose the DT values of as much as you want because of the limitation of the processor and so on. Because the processor will tell you what is the least sampling value you can select. So you can see that both of them are working fine. We have seen, and different speed of around 30 RPM, it is fine. So now what I will give you here is I will give you this particular model to you. I will after the lecture, and you can play around with this model and you can see what is happening. So this is what the Kalman filter, extended Kalman filter, how it is working. The plant can be the non-linear one. It can be any non-linear plant. I will show you how the plant is. Why I am saying it is non-linear? Because you can see that there is a product of two states here. Can you see the two states, or it is very tiny to see? You can see the product of two states. The U1 and U2 are the two different states. So there is a product term. So that's why it is a non-linear. This plant, what we assume is a non-linear. In the first state, in the second state also, U1 square is here. This is U1 square. So that's why my plant is non-linear. So I have to find the Jacobian for this one. And in its form, this non-linear filter, if you want to use a you should have the Jacobian. And in how we calculate the Jacobian also we have seen. So this non-linear plant and this non-linear extended Kalman filter, and this what you can see here is called as the discrete time integrator. So this basically uses the Euler approximation what we discussed, and the output of this one will be the discrete one. So this is the whole story about the Kalman filter. So now what I will do here is if anybody is having any doubts in this Kalman filter, please let me know. This is the time to interact, because I'll be going next to the whole summary of the particular lecture what we have discussed. Already, because of due to technical issues, we wasted around 20 minutes. So today we don't have much time. Yeah. Anyone is having any doubts on this Kalman filter?
Sir, initially I missed something, but
Okay.
I have a question, sir. So
This is the
we
last
have
question,
to
Srihari,
initialize
because two questions.
covariance matrices.
Yes.
Okay.
Yes.
Sir, how do we
The initial uncertainty.
initialize
Yeah, I'm telling you
covariance
that depending
matrices
upon
as
how.
per the plans?
Yeah. Yeah, I'm telling you. If you know that if your system is highly uncertain, if you don't know the initial condition of the plant and the condition of the estimate, then in that cases, what you have to do is you have to keep the initial covariance as large as possible. So that will tell about the initial uncertainty about the states. That means if you generally, if I am saying that state values, then your covariance you can start with very small values and you can propagate. In some cases, you don't know where is how far your initial state is from the initial estimate. If that is the case, then you have to take the very large value of p values. In more specifically, in this particular case, what you should do is the initial value which is coming. This is the
Okay.
discrete integrator. You can the initial conditions. Here is the initial conditions. Here you can give the initial condition of the plant, and whatever the initial condition of the plant and estimate whatever you are assuming, the error should be reflected in terms of the uncertain initial covariance. Plant estimates are very close.
Mm-hmm.
Choose the very smaller value of p. If you don't know what example of ISRO's or NASA's re-entry launch vehicle, suppose if it is entering into the atmosphere and you want to calculate the position and velocity or the location of the particular launch vehicle from the particular bias radar, some uncertainty because your radar may not exactly the percent. So at the time you can choose the initial uncertainty is very large, and then the Kalman filter should try to, as the time propagates, it should try to minimize the covariance as much as possible. That is what eventually for the stable, once it reaches the stable, everything is stable. If your control is stable, plant is stable, then you can see that this covariance will become very least, will come to the very least value, and there will not be any variation in the covariance and so on.
Okay, sir.
Yes. Okay.
Okay, sir.
Okay. So
Thank you,
I'm
sir.
going to, yeah. So let me explain. So each day what we discussed, I will explain in each of the 5 minutes. So the pre-FDP session I have conducted for the faculty or the participants who have not attended FDP 1.0. For them, I have conducted the pre-FDP session. There we have discussed control system past, current, and future, and some challenging control problems and PID control design, a toy example, a very simple example. And then we have gone for the pole placement, LQR and LQG control. And then we have discussed this particular paper where it was an LFC control and there were two PID controllers. And we have seen that the Kundur, he has used only integral control. If you use the PI control, what are the advantages? And we have compared the same and we have used the auto tuning, a 1 minute, that's what I say that 1 minute tuning, 1 minute we have seen how to get the desired response. And we compared that with several of the papers where the people have used the bacteria foraging optimization method, PSO method, and so on. And we have seen that it is able to get the better results from them in 1 minute. And on the day one, again, I have repeated briefly the PID controller, pole placement, and LQR controller, and we have done the simulation of this particular plant. DSP-based implementation of an LQR with integral action based reverse shunt active filter (SAF). And we have seen that the LQR controller is not enough, so we have gone for the tracking because it is a tracking problem, it's not a regular problem. We have taken the integral of the states which we want to track, LQRI we call it as LQR, linear quadratic regulator integrator. So that integral action of the particular state we have considered for the tracking purpose, and we could able to replicate the results as well. And I given you the skeleton code as well, and most of you could able to do this particular. We could able to replicate the results in this particular paper. So you see, slowly we have moved. So earlier, so now it was a 2008 paper, and slowly we have gone till 2020 paper as well. And in the day two, what we have done here is pole placement and LQR analysis, a toy example on linear and variable structure control. So what we have seen that we have taken the example of double integrator, and we saw that double integrator plant, if you use the linear controller, two different linear controller, it couldn't able to stabilize. That means from some initial conditions, it is not coming back to the equilibrium point in the absence of control. So that, however, if you use those two controllers together by changing the structure, which is called as a variable structure control, then we can able to see that from any initial condition, it is possible to bring those initial points. And we have seen how the spiral effect is coming into the picture, and you people have done the simulation as well. So that was a small toy example. So that tells about the importance of the variable structure control. That means two linear control independently they work. If they act, then they couldn't able to stabilize the system. Whereas if we combine both of them and the structure is different, then we can use then we can ensure the stability. And then we have gone to the sliding mode control, and we have compared the linear state feedback law and the sliding mode controller. We have done some simulations, and these two papers we have simulated. The first paper is ITP transaction and power. You can see that slowly we have moved to 2010, and we have seen that for the same concept they have applied to the cup converter, a Q converter in 2012, And almost the structure we discussed everything, the numerical aspects in these papers in a very detailed way. And I gave you the skeleton of the code as well. And most of you have replicated the values, the results, whatever in this paper as well. So once this is done, on third day, we have gone to the Leuenberger observer and sliding mode observers. So this Leuenberger observers, we generally it happens, it works on if the plant is nominal and there are no disturbances and so on. This Leuenberger observer is the best one. That's what we have seen. And we have seen the sliding mode observers as well. As soon as the disturbance or unknown disturbance comes into the picture, sorry, then the sliding mode observer is capable to reject that uncertainty up to certain certain class of uncertainties can be rejected. And we have seen the Leuenberger simulation with and without disturbance. And without disturbance, Leuenberger as well as sliding mode gives us the same state estimate. However, as soon as the disturbance is introduced in the plant, and you can see that you can assume that we have seen in the simulations that Leuenberger observer loses its properties, whereas the sliding mode observer retains the stability. And we have seen with disturbance and without disturbance. And more specifically, we have simulated this particular paper, IEEE transactions on industrial electronics. It was 2019 September paper where we have seen, how to estimate the state using the sliding mode observers. And the skeleton also, I think I have given for this particular paper. And when we proceeded to the next day, day 4, and we have seen a very important aspect of sliding mode control or the sliding mode observer. And we have seen how to reduce the main problem with the sliding mode is scattering because of the sign function what we are using. And there are many other ways to, if you want to publish a paper, then you have to go for the higher order sliding mode control, making the things very complex and so on. But industry doesn't want that. And I have shown you that in 1 minute, how to reduce the chattering. And we have seen in the simulations as well. So you all have done the simulations, and you yourself has could able to see the difference. That 1 minute is the delta that we are trying to approximate that sigmoid function with the delta. And the delta basically tells about the kind of tolerance about the sliding surface. And if the delta is large and there is some trade-off, but delta of 0.001 we have taken, and immediately the chattering has gone away. And we have seen two different papers, and we have simulated this particular paper as well, LFC for interconnected power systems, where and next we have used the unknown input observer state and fault estimation. So till now, what we have discussed about the states itself, but so this unknown input observer try to reject the unknown inputs. You should, if the inputs or the disturbance is known to you, then how to estimate the states, which in such a way that your disturbance should not affect the state estimate. That's what we have derived, and we have solved that one as well. And again, we have done this fault estimation as well. That fault is what is the fault coming to the unknown fault, and how to do the estimation also we have done. And we have verified that very high frequency of sinusoid and uncertain faults also we could able to estimate. And the simulations, we have seen that simulations for the LFC for interconnected power system using unknown input observer. We have discussed how to estimate this one, and I think some of you might have solved this problem as well. So this is published in IEEE Smart Kit, and Dhananjay has told that they have not done the state fault estimation. They have only shown the effectiveness of the state estimation in the presence of disturbance. However, by using the single line code, we can estimate the faults as well. That's what we have learned. And another paper, this is my paper, we have seen the another class of where the information is coming from multiple sensors, and correlate versions also we have briefly discussed. Suppose if your sensors are of limited precision, or if your processor is of limited precision, then how to get the more accurate estimations, that also we have seen briefly. And on the day 5, we have discussed what to do with the reconstructed fault signal from the UIO that gives us the fault compensation or the fault detection. And we have discussed the Lyapunov theory in general. There are two different Lyapunov theories. One will deal with a linearized version, and one will directly to the non-linear system. In very naive forms, consider the positive definite as Lyapunov positive definite, and you should ensure that the derivatives of it should be the negative definite. And we use the concept of Lyapunov theory to develop the backstepping lecture and a toy problem, and we have manually did the backstepping. We have simulated for the single order first order system, and for the second order system we have manually derived the backstepping controller. So, and we have seen how what is the meaning of backstepping, and the simulations we have seen from this paper, and I think we're able to replicate it. Is exactly what we have discussed in pen and paper. The same thing they have done here as well. And in the day 6, we have given the brief explanation to the extended Kalman filter, and the simulation is also been and is also been discussed. And let me see. Okay, and I will share you the simulation with you so that you can run at your home and you can do whatever you want. You can extend this work for things. So that is one from my side. 5 minutes is there for the discussion, and then we will have the validatory and feedback. So I will be giving you all these things. And one more thing, all of you please note that the codes what I have developed in the last 10 years, which is in my book, Nonlinear State Estimation Applications, Theory and Applications. I will be circulating to all. I will be keeping it to the outside world. In a week time, the whole my hard work for 10 years, I'll be giving to the research world for free in a week time. I'll be giving you. I will share with you as well. So you can use the complete code. So I don't want the researcher to start, from zero. So they can start from where I have made my research. So that will be helpful for every. So I'll be sharing in a. I'm just taking the code and keeping everything ready. So in a week I will share with the outside world. So anyone can use this code. The code will have very advanced versions of Kalman filters, uncentered Kalman filters, cubature Kalman filters, cubature information filters, cubature H infinity filters, and all everything whatever is in my book I'll be sharing with the whole world. So you can also use that. So quick 5 minutes is there for the questions, and then we will start the valedictory. And as I told, there will be big final quiz as well. Today I have gone very fast, I know, but 20 minutes we lost with this technical issues. So this is the first time it happened in the last 6 days. So I'm sorry for that one. It's nothing that I can do, anything about it. Yeah, so 5 minutes. If you have
Sir,
any questions regarding, yeah.
sir, good evening, sir.
Yes.
This is Apparo from Venkateshwara College of Engineering, sir. Technology.
Yes, sir.
Sir.
Good evening, sir. Good evening.
Good evening. Sir, my colleagues missed that 1.0, so that very soon you are launching that for student SDP, na? For that, our faculty can register or faculty can register.
Anyone can register. Anyone can register, sir. There is no such limitation. Anyone can register.
Thank you, sir.
Yeah,
Thank you.
for your information, as sir has reminded me, I'm starting the SDP Student Development Program 1.0, where from the scratch I will start how to build the models, the Simulink, and how to design PID controller, how to design pole placement controller. I'll be considering 3 different examples. One is DC motor, the second one is boost converter, and the third one is the single machine infinite system SMIB. So if any of your students are interested, please ask them to register. I might limit it to 200 itself, 250 people itself. So as I already the flyer I have circulated, if any of your students, if you think that they are interested, or even faculty as well, they are welcome to register for that one.
Thank you, sir. Thank you.
Hello, sir. Hello.
Yeah. Please.
Hello. Sir, why you have taken 2 plants in EKF? Why you have taken two plants in EKF simulation?
2 because
2 plants.
Yeah, I'll be showing. Did I close that one? Yeah. So this is only the complete plant with the full state feedback. That means I assume all the states are available. This is the full state feedback. And here, this is the estimated state feedback. You can see that the estimated value, whatever is coming to the plant. So this is based on full state feedback, and this is for the estimated state feedback. Because I want to compare my responses, right? So that's why I have taken this one. It's just for the comparison. For the practical system, it is not available. I assume that I have whatever the error I have shown here, it is quite minimal. So up to the 0.35. So in the practical cases, this is not available. So this is just to compare, if it is not available, then you don't know what this error, right? Because you don't know the exact value. So this is just to show that whatever you have designed is perfect. In the practical system, this is not, in general, it is not available. To assume, based upon certain other things, what is the error you are getting from here. Error calculation need state as well as estimate. Since you don't have the state, uh, since if you don't have the state, then you have to assume certain things, and based upon that, you have to think that since it is working here, it will work in the real cases as well. And combined state estimate, combined control and state estimate, I will just briefly throw you some information, some ideas. This is the one. Generally, the control and the state based upon this, the control and the output, you get the state, and this estimated states, goes to something, and the estimated states is given to the controller. So this is what in the real scenarios it works, real industry, you know. So this is the thing. Yes. So anything else? And this is the LQG, which is a combination of LQR and Kalman filter. Can you able to see my screen? LQG.
Sir.
Okay. LQG is LQR plus the Kalman filter. This is what we had discussed as well. If the state estimation is Kalman filter and this control system is LQR, call it as an LQG. And we have seen what is linear quadratic Gaussian, and we have seen that LQ and LQG, what are the differences. And if it is not satisfying, then transfer recovery. If it doesn't ensure this uh, guaranteed margins. So that's it from my side, and thank you all for your patience. So if you have anything, another couple of minutes we can discuss. I know that today I have not given you time for the discussion.
Thank you very much, sir.
That I promise that.
Thank you, sir, for such wonderful
8 o'clock.
session.
Yeah, please be live for another couple of minutes. I will ask chief guests, and then we will take break. And as soon as this feedback session is over, I will activate. Why I'm saying it is very important. As soon as the feedback session is over, I will activate the quiz link, and I will not give you more than 30 minutes to solve that mega quiz. Okay, so that's why it is very important to know when the, because now we don't in the system, we don't know when this feedback session will be over. As soon as it is over, I will activate the quiz, and from then only 30 minutes will be live. So just a couple of minutes, and then I will ask, we'll start our validity, and within 10 to 15 minutes, we'll complete everything.
Barney, good evening. Barney, good evening. Barney, Barney,
I just called the guests and they will be joining.
Barney, good evening.
Good evening, sir. Good evening. You able to listen, sir?
Can you listen now? Hello.
Yeah. Hello, sir. Hello.
Hope you can
Hello,
hear
sir.
me
Can you
now.
able to listen? Hello. Yeah.
Yeah.
Rajesh, are you there, sir?
Barney, good evening, sir. Good evening.
Good evening, Raja.
Yeah.
It's just Hmm. So hope
Things
you
what?
are well.
Yes, sir. So it was a 6 days FDP, and around 120 participants have registered for this one, and almost most of them have joined, and
Okay.
it went very fine. So though the time was 6:30 to 9, but we never ended at 9, and it was it was seamless. This thing.
Okay.
Uh, so so welcome you, sir. So if you
Yeah.
can,
Thank you.
you know, and if you can just address our gathering for a minute or so, both of you.
So good evening, all of
Hello,
you.
sir.
Yeah. Good evening. Shall I go ahead?
Okay.
Yes, sir. Yes, sir. Please, sir. Principal, sir.
Okay. Okay. So, good evening, all of you. At the outset, I'd like to compliment the entire team for conducting the FDP on the control systems 2.0. I think this is the second series in the season, if I'm not wrong, and I'm sure that
Yes, sir.
the
Yes.
first series and with the same tempo, the second series also went on. I really remembered the feedback session what you had at the end of the first session when you had. So I'm there almost throughout the participants giving the feedback. They have expressed a fantastic feedback, and I'm sure that this program also went all in the same tempo and with the same learnings. And I'm sure that all the participants have learned almost beyond their what is that the domain as far as the academic domain as far as their topics are concerned. And I'm sure that the learnings whatever they have will be useful for them for taking the sessions to the students post COVID. And let us hope that whenever say now almost it is something like uh, you know, from hereafter we always talk about pre-COVID and post-COVID. So COVID will become a COVID-19 is becoming like a what is that a timeline where we always start referring in the future. Probably our generation had that what is that the facility of referring COVID, and also a fancy year 2020. So in fact the post-COVID sessions, we're not very sure that when the classwork is going to take off, and when the students will come back normally to the college, and when the sessions will go on. And this time that is available for all the students and teachers need to be used very effectively. And I'm sure that your team is keeping everybody busy, keeping yourself busy in learning, and at the same time you're also keeping the students busy, engaging them, and then keeping them in the tempo and maintaining the tempo. I'm sure that the lockdown is going to give a lot of learning opportunities for both students and teachers. So I once again compliment the entire team and wish you all the very best.
Yeah. Thank you. Thank you. Thank you very much for your compliments.
Thank you.
Now I request Professor Rajamurgadas, Professor Rajamurgadas, Vice Principal, to address the gathering.
Thank you, Bernie. So I think it's giving a different kind of experience for a validatory function in the late evening hours. And first of all, let me appreciate the entire team and particularly Dr. Bernie for taking this initiative, FDP on Control Systems 2.0. So one observation what I could find during this lockdown period is, initially when the lockdown was announced, maybe on the late period of March, many of the colleges across the country started floating webinar, FDP, and so many things. And every college has given a mandate, and people started joining in all the webinars and other things. But after a period of time, I could see that the tempo has been slowly reduced because they earn the certificates, whatever they require. But this FDP 2.0, I'm very pretty sure that you have a crowd. Actually, really, they wanted to learn in my perspective, actually. So in that perspective, I think keeping the tempo in Control Systems 2.0, I think you have a good crowd who has the real passion to learn the things. So in that perspective, really appreciate the organizing entire team as well as the participants in a bigger way, and hope you have enjoyed the session. The session went, I think, in very religiously with all the things, and your attendance is also very good, I was told. And the session went up to even late night, maybe 10:30, maybe a couple of days back.
Now the participant strength is close to 100 now.
Yes. Yeah, that's what I'm telling. Though, see,
90%.
since the program, see, now the participation in FDP has drastically come down, actually. As I already told you, the participants have registered in many of the programs only for the want of certificates. The real thirst, the real passion of learning the new things has gone up, actually. So, but this crowd, I'm very pretty sure that this is the real crowd, what you are really looking at. They got the passion to learn the new things. So in that perspective, I particularly congratulate and appreciate all the participants for their effort. And I congratulate Dr. Barani for taking this good initiative. I think this initiative should continue like X.0. It should continue in the coming days also. Say I'm particularly mentioning X.0.
Yeah.
So
yes,
don't
sir,
stop here. X is unknown number. You can have any number of some programs. Even the participants who attended 1.0 and 2.0 also can register in 3.0 to reinforce the knowledge so that you can be specialized in this particular domain. So I appreciate. Wish you all the best. Let us looking for another valedictory for 3.0. Wish you all the best, Barney, and your entire team. Thank you.
Thank you, sir. Thank you.
Barani, I have one just a suggestion here. Since this series of programs are coming up, and earlier also the program was more than right. So now it is for 1 week. If you are really looking at, let us say, 3.0 and 4.0, you can now give announcement stating that all the faculty who are there appeared for all the four series, and we have an assessment at the end of the four, and they'll be given a certificate.
Yes, sir. The
They'll
complete
be given a certificate. They'll be given a certificate for the complete course,
kind of
where
nano course, nano.
that can be taken as a very value-added credential.
Yes, sir. Yeah,
And we
sure,
can
sure.
also validate that. We can also get it validated by the authorized
Yes, sir.
agencies
Yeah.
as well.
Yeah, sure, sir. Sure, definitely,
When we
definitely.
do the things in a series, sequential and in a series, I think we can validate, and then that validation always will give a lot of motivation for the people to participate.
Yes, sir. Yes, sir.
This
Definitely, definitely.
Bharani, this particular crowd, what
Yeah.
you are having is a promising crowd actually.
Yes, sir. Yes, sir. It is.
That is what I'm telling. Sometime back, I floated one
Yeah.
program around 1,500 participants registered. I was really wondering how 1,500. But when we float on payment basis, the number has drastically come down exponentially.
Come down. Yes, sir. Yes,
See,
sir.
that is what I'm telling. You have a good crowd, maintain the tempo. Nothing is free
Yes,
of
sir.
cost in this world. I think you have done a very good job. All the best, Bharani.
Yeah. Thank you, sir. Thank you. Thank you, sir.
Good luck.
Now we will. Yeah. Thank you, sir. Now we are open for the feedback, a few feedbacks, and then there will be grand queues after the feedback sessions. Now it is over to you,
Hello.
participants. You start.
Bharani, I'm signing off. Yeah.
Hello. Hello.
Bharani,
Yeah.
bye.
Yeah.
So
Bye,
Yes, sir.
sir.
Yes, sir. Bye, sir.
Good luck.
Bye, sir. Bye, sir. Bye. Yeah. Thank you, sir.
Sir,
Yeah. Hello.
Hello, sir.
sir,
Yeah. Hello.
I give you feedback.
Yes, sir.
I'm
Yes, sir.
Amaran.
Please tell your name, where your institute.
Yeah, I am B. Amarendra Reddy, working as assistant professor in the Department of Electrical Engineering, AU College of Engineering, Andhra University. Yeah, this is the first time I attended Bharani sir's lectures and FDP program. Whatever sir is working, I just started working in the same area since 2 years. And we also have one course in sliding mode control theory. That's why I could able to follow some of the concepts what sir told. And I was impressed, and I wish to register for this particular program. Why? Because I am following the sir's guide textbook, and it is one of the best textbook in the world for the sliding mode control theory, under whom Bharani sir did PhD. That's why I wish to register for this, and I wish that sir has made the requirements and expectations to my level, and he is one of the most good resource person as far as sliding mode control theory is concerned in our Andhra Pradesh and also in the southern region. One of the best resource person, and we feel to have a great person in our region. People, and he is also sharing valuable information, and also he is giving very good information, and he is giving encouragement. And we also I also given some so preference to work with him, if probably if I'm doing my work in IIT Delhi, so after completion fully I will work with him if sir permit. Sir is giving very good information. So thank you,
hello.
Thank you, sir.
Hello.
Thank you, sir.
thank you.
Yes,
Hello.
yes, sir.
Hello.
Yeah.
So this is
Yeah.
Dr.
Please tell,
Sharath.
sir.
Hello.
Yeah. Hi.
Is it audible?
Yeah. Hi.
This,
Yeah.
this is
Yeah.
Dr.
You are
Sharath
audible. Yeah.
from Sri Vishnu Engineering College for Women, Bhimavaram.
Yeah.
So from the past 2 to 3 months, I am continuously attending many FDPs, sir. But this faculty development program organized by you was the best, sir. See,
Thank you.
I worked on extended Kalman filter for nearly 6 to 7 years, and I completed my PhD from IIT Hyderabad. And again, I'm thankful to you to brush up my basics once again, so that I can able to recall what I have done from the past few years. So I will go
Yeah.
ahead based upon the suggestions given by you. Thank you very much, sir, for this nice FDP.
Thank you. Thank you. Thank you. Thank you, sir.
Sir, this is Satya from IIT. Yeah, hello.
Yeah, hi. I think someone is talking.
Yeah, sir, can you hear me?
Yeah, I can hear you. I can hear you.
Okay, just make it fast. So this is Satya from IIT Bhubaneswar. Regarding the FTP and the content, I have to say only one word: it's awesome. Because I enjoyed it. I enjoyed it a lot compared to learning and all the things. I think I have to say a few words about Barney sir because I have known this through my friend Mr. Vikas. If sir remembers, he is a student in his post graduation, and currently he's in NIT Roorkela pursuing PhD. So I think from past 2 years, I and Bernie sir know each other in names. Like he's a messenger between us. So we did not talk or we did not discuss or we did not interact anytime. But I think through this FDP, we just had a lot of discussions, a lot of exchange of knowledge. I have personally also contacted you regarding some details and materials and etc. So at last this day comes. So where I could just directly talk with you and you also directly talk with me. So I hope this kind of events will happen further from you, and I hope that at instances required, we also have that knowledge sharing platform between us. Thank you.
Thank you, Satya.
Excuse me, sir.
Yeah, hi.
Hello, good afternoon. Hello.
Yeah,
Excuse me, sir.
I think one at a time. Maybe the Ramesh can now talk. Ramesh Babu.
Yeah, sir. Yeah, this is Ramesh
Yeah,
Babu from Saint. Yeah, sir. Am I audible, sir?
yeah. You are.
Am I audible, sir? Yes,
Yes,
sir.
you are
I'm
audible. You are
Ramesh
audible.
Babu from Saint Anne's Engineering College. Yes, sir. Yes, sir. When compared with this, I'm little different. I'm not working in the area of the control area of the control systems. A special electric was happen to attend one but the college during already in the line that it was listen to happen really I was in deep so and I joined this HCL express 0 is basically who started from really from control to understand not for the control systems but 30 to 40 point.
Yeah, hello. I think
Hello.
I cannot able to hear anyone. Yeah, hi.
Hello. Good afternoon. Good evening or good afternoon. Hello.
Good evening. Yeah. Good evening.
Okay. This is Kasim from Nigeria.
Hi, Kasim. Yeah.
Okay. I want to start by appreciating the presenter, Dr. Barani, for your wonderful, educative, and very informative lectures. I'm a student of actually signal processing, but I developed interest in control engineering just of recent. In fact, I want to go into control engineering for my PhD studies, and most of the things are sort of new to me. theoretically, I've gone through it, but practically, I'm able to see it, and I truly appreciate all the lectures. And I want to thank you for the consideration you gave to us here in Nigeria, and we appreciate your work, and we appreciate your lectures, and we definitely build knowledge. Thank you very much. Thank you again, and thank you very much.
Thank you, Kasim. Thank you very much.
Good evening, sir.
Good evening.
Myself, Guru Prasanna, sir. I am from MAS Engineering College.
Yeah, hi, Guru. Hi.
Hi, sir. Actually, I'm teaching control systems, but my
Good,
PhD
good.
project is in power quality issues,
Okay,
where
okay.
I used sliding mode control for 10%. That 7
Okay.
years back, I did my MTech, and I studied only 10% only. So because of your FDP program, I would like to, I can able to learn nearly I think it is 40%. So
Thank
thank
you,
you for
sir.
the well organized program. I hope you
Yeah,
have a
thank
bright
you.
future in sliding mode control. As somebody give you a review, you will definitely
Yeah,
a
thank
good
you.
expert in sliding mode control, sir. If possible,
Yeah.
you plan for 3.0, where most people maybe triple number will come. For, Alright. Thank you,
Yeah.
sir, for the organizing, and special thanks to GM Institute Management of the GMR Institute of Technology. Right, sir. My
Thank you.
regards to all, sir. Be safe.
Thank you. Thank you. Thank you, Guru.
Welcome.
Hello, good evening, sir.
Good evening.
Sir, myself, I am Dr. G. Kusma. I am working as assistant professor in SRK
It's
Engineering College.
it's echoing. Kusuma, it is echoing. It is echoing. I think you are logged in from two devices.
Okay, sir.
Yeah, it's better. Yeah.
Sir, is it audible, sir?
Yeah, yeah. Yes, it is audible. It is audible.
Okay, sir. So this is Kusma. I'm working as assistant professor in SRK Engineering College at Bhimavaram. And first of all, I will thank your organization, sir. There is a good FDP programs are conducting. This is the first one. I've also attended FDP 1.0 as well as an FDP 2.0. I'm already working in, and my specialization is also the control system. In that particular area, what I've seen in here, now also I extended that my research work with modern controller, which they were Thank you very much, sir, for sharing a hands-on conversation knowledge. Every day I learn new things. Definitely helps me to go forward in my career.
Thank you. Thank
I
you,
think
Kusuma. Thank you. Yeah, yeah. Sorry.
sir.
Yeah, your voice is disconnecting. Your voice is getting disconnected. I don't know
Yeah,
due to some reason.
I'm also again. Thank you, sir. Thank you very
Okay,
much.
okay. Yeah, welcome. Thank you.
Hello. Good evening, sir.
Hello. Good evening.
Good evening, sir. Myself,
Good
Dr.
evening. Good evening.
Bhagwat Panda. Hello.
Yeah, yeah. Please tell,
Hello.
sir.
Sir, I am
Yeah, please
working
tell, sir.
associate. Sir, actually, I am working associate professor electrical department, Palamajin College, Government College, Berhampur. Though I am power system engineering, but today your 1 week program, I have gained so many control system engineering. Actually, I am very thankful to you. Sir, thank you for organization also. If you again you do 3 point, I can also attend. Thank you, sir.
Okay. Thank you. Thank you very much. Thank you. Okay. Okay. Then I think if
Good evening, sir.
if good evening. Good
Hello,
evening.
sir. Good evening, sir.
Yeah.
Am I
Good
audible,
evening.
sir?
Yeah. Yeah. You are audible.
Am I audible? Sir,
Yes. Yes. Yeah.
this is
You are
myself.
audible, sir.
My name is Subramanya Rao, sir. Working as a lecturer
Yeah.
in
Hi.
Government Polytechnic College, Vizianagaram. Basically, I
Yeah,
passed
hi.
out my engineering in 1995, sir. Almost 25 years
1995.
over, sir. 95, sir.
Uh-huh.
At present,
Yeah.
I am working as a lecturer in Polytechnic College. Basically, we are dealing with diploma courses only.
Uh-huh.
Due to some reasons, now I joined in my MTech course in Visakhapatnam through my college. They give permission, and I'm doing my MTech in
Uh-huh.
power systems, sir.
Okay,
Through
okay.
my
Nice.
actually, I made that feedback also in the feedback from first day, sir. I think you might have
Yeah,
observed, sir.
yes. You told that there
My
is
sir.
some technology lag. Yeah, that's what I
Yes,
can
sir. Yes,
remember.
sir.
Yeah.
But
Yeah,
anyway,
I remember.
the way you approached this entire program is very useful for me, sir. But basically, I want to attend the SDP 1, sir. Today morning, I just received your mail, sir, and I
Uh-huh.
registered that program also, sir. Actually, I want to
Sure.
learn from the basics, sir. But my
Mm-hmm.
case is reversed, sir. Actually, I attended the first 2.0, but I don't know anything about the control system right now because of long gap.
Uh-huh.
But anyway, I'm planning to
Yeah.
attend that FDP after seeing your presentation, everything, sir. It was very nicely
Mm-hmm.
organized. I am the first. This is the first time, and just even though I attended all the days, but I got only 10% because of my lagging only, sir. Not your fault, my lagging. But
Mm-hmm.
I'm planning to attend that FDP one. I will try to recollect these things also. And thank you very much for giving me this opportunity to attend this program, sir. Once again,
Yeah.
I'm thankful to your principal, sir, Prasad Garu, and vice principal, sir, Raja Garu, for allowing me this to do this program, sir. Thank you very much.
Yeah.
And once again, the main thing I like from your teaching is the way you are explaining the papers. But nowadays, nobody will explain the papers particularly. Daily, you are explaining
Everybody
the
want
two
to hide.
papers.
Everybody
Yes, sir. Yes,
everybody
sir.
want to hide the knowledge what they are getting because
No, sir. No, sir.
that
That
is
is exactly true, sir. But
because
in the last also, you told that you want to express all the means share all your whatever the things you have done in the past 10 years. That I am very much
yes.
thankful for this, sir. Thank you very much, sir. Thank you very much for
Yeah.
giving this opportunity. Thank you, sir.
Thank you, sir. Thank you, sir.
Hello.
Yeah. Hi. Hello.
Hello. Good evening, sir.
Yeah. Hello.
This is
Good
Lakshman,
evening.
sir, from Rajiv Gandhi University.
Yeah. Hi, Lakshman. Yeah. Hi.
Hello, sir. The way FDP is planned, it is very nice, sir. Actually, a lot of hard work and dedication. It is possible only because of your lot of hard work and dedication. I am really thankful for you for sharing your knowledge, and I thoroughly enjoyed all the sessions, sir. Thank you very much, and I'm waiting for next. Next 3.0.
Yeah. Thank you, Lakshman. Thank you. I don't know when I will conduct, but at least not in a month. Maybe I have to see the other responsibilities as well, and then if time permits, I will go for it. Thank you.
Hello, sir.
Hello. Yeah. Hi.
Sir, good evening, sir. So actually, I have attended earlier FDP 1.0, sir, control systems, your session.
Uh-huh.
So during
Yeah.
1.0, actually, I am okay. I am good at the control systems for UG course, sir. But
Mm-hmm.
when I started attending this FDP 1.0, first 3 days it was okay, sir. I can able to understand, analyze the things through simulation and whatever the coding. But at the fifth or sixth day, I am unable to understand. I mean, the concepts are day by day they are increasing the complexity at
Yeah.
that time. So I am unable to understand at that time. But I whatever the recorded videos that one I have gone through, sir. So somehow I can analyze. But now again attending this FDP 2.0 your session, so I can able
Yeah.
to if I go through those topics now, I can understand it easily, sir. So because
Yeah.
this time you have planned in I mean obviously 1.0 is a very good session, sir. At the time I was lagging behind some concepts in the control systems,
Uh-huh.
so advanced topics.
Mm-hmm.
So now I am able to follow all the 6 days sessions, sir, and able to do simulation whatever you have explained regarding the skeleton codes already. So I thank, sir.
Yes.
I thank you very much. You are explaining whatever the doubts all the participants are asking, and even though it is of late, As a one-man army for the second time, you have done a great job, sir. I thank you for that, responding all the queries. Mm,
Yeah.
okay. So I will
Thank you.
be actually I have stuck at that my research, sir. Actually, my research side is power systems, so I am working on it.
Uh-huh.
So fault identification, that's it, sir. So both the transmission
Uh-huh.
side and the distribution side with the renewable
Distribution
energy.
side.
Yeah,
Uh-huh. Good,
with
good, good.
renewable energy, including the so,
Yeah, yeah.
but regarding the renewable energy, we need to have a different controllers are coming up, sir, nowadays. So when we see the
Yes.
literature,
Yeah, of
so
course. Yeah.
through this FDP 2.0, I can observe which I mean in the literature survey where I can choose or sort out my exact controller, and I can have a control over through this FDP 2.0, so that I can manage all the steps, making the system stable to
Yeah.
my research area through this FDP 1.0 and 2.0, sir. I thank you very much,
Good,
sir.
good.
Okay.
Yeah, thank you. Thank
Okay,
you.
thank you, sir. Thank you.
Thank you.
Okay.
Thank you, Mujir. Thank you.
Thank you, sir.
Thank
Thank
you
you,
very
sir.
much.
Thank you. If there
Thank
is,
you.
if you are planning for FDP 3.0, I mean, whenever, as the college is,
Yeah.
as you mentioned earlier, the responsibilities are also there. So when you are
Yeah.
mentioning, when you are planning for this, kindly post a message in that FDP 2.0 group, sir, WhatsApp group, so that
Sure, sure.
we will be
Definitely.
benefited.
Definitely.
Definitely.
Yeah,
Okay,
definitely.
sir. Thank you very much, sir. Thank you.
Yeah. Yeah, definitely. Thank you.
Okay. Thank you.
Thank you. Okay. Okay. Okay, all.
Hello.
So
Hello.
now, yeah, hi.
Hello.
Yeah, hi, Ab.
Sir. Just now I spoke. So I forgot to say one thing. As the workshop
Yeah.
itself a unique hands-on, so the lecture
Yeah.
also went on a unique way, where without any disturbances, in a smooth way.
Okay.
So waiting for the third workshop, it will be, sir. So now we have completed two successfully. Waiting for the third one, sir,
Yeah.
which will be a hat trick for us to learn more from you, sir.
Thank you. Thank you. Let's let's
Okay, thank
let's
you,
hope for
thank you,
the
sir.
best. Thank you. Let's hope
Yes,
for
yes,
the
sir.
best.
Okay, yes, yes.
Yeah. Thank you. Thank you very much. So I think so now we can uh, wind up this validatory session. So I will tell one or two points. Just I will not take more time. Just a couple of points what I want to discuss here. The way how we started and how we ended. The first day, I have pre FDP workshop. I have given you the videos, the PowerPoints, the slides, everything, and then I have asked you to do go through that one so that you will be everybody will be in the same page irrespective of you have attended the FDP one or not. So that was what we have started in the very FDP pre-FDP session, which is on 2nd of July, and then slowly we have moved on to the first day where we try to solve some papers, some existing papers, LFC and other things. So I started giving you the skeleton code in the very first day with complete information. Only what you have to do is just copy and paste the content from the slides and the code will run. So that was the first stage, stage number one. In the second stage, what I gave you is I instead of giving you the skeleton thing, I gave you the skeleton, but I instead of the text, I copied it as an image, the code. So in some cases, you have to type unless you are using some advanced software to object to image recognition to other character recognition so on. So there you have to manually type something. And the third stage is what I did is I have not given you the skeleton, and I have not given you I have not given you the skeleton, but only the diagram of the Simulink and the code, both of them. So you could able to replicate. And in the next stage, what I did is I haven't told you the code as well, and I asked you to do the simulation on your own. And the final stage is I have not given anything. I have not given anything. Only the paper I have given, and I have and I'm asking you to replicate. Some of you have already replicated some of the papers. So this is a step-by-step approach. After several iterations, I thought myself what could be the best, so that at the end you should be on your own. So because after this FDP, we are all there to help each other, but in some cases, you have to be on your own. you cannot be depend as far as the research is concerned. Sometimes you cannot depend on the others. You have to do your own, because as you keep on going into the intensive research areas into very deep, then nobody knows better than you, and you should be knowing how to debug your code, how to write the code. So that was my main purpose, the solo purpose, to make the things bit and bit tough and tough and tough. And finally now I think at least you can, some of you can, do some simulations from the papers to make the things easy. So that was the approach what I had adopted. Maybe during this time you might have struggled very hard, and you might have frustrated as well because others are getting the results, I'm not getting the results. That's what some have sent me the feedback. But that's how the life is, so that's how the life is. Slowly we keep on learning the things to become the expert in some area or so. That is one thing. And yeah, so thank you all. And the second thing is, if anybody wants to collaborate with me, so the same thing I have told in the FDP one as well. The two cases, I'm always happy to collaborate. If the one is who has not registered the PhD, and the second case is those who have completed the PhD or submitted the thesis. Those who are pursuing the PhD, then I am a bit hesitant to collaborate, because it need approval from your supervisor, and I don't think supervisor in general, they have their own egos. They want yeah, they want, if any of your supervisors is really interested to collaborate with me for your PhD work, then ask them to write an email to me. And I know that it will not happen. So that case, if you are pursuing the PhD, then I'm sorry that, unless your supervisor agrees and sends me an email, I'm ready for the collaboration. Otherwise, no. I'm quite straightforward in this aspect, because later on you should not face any problems because of that one. And yeah, those who have not started the PhD, or who have completed the PhD or submitted the PhD, I'm quite open to collaborate. For those people, I'll be sending you the 4 papers, like what I did, 3 or 4 papers, and try to get some initial results, and please send me within a week time. If I will be sending the papers today, within a week time, if you could able to send me at least some partial results also from those papers, then I am open for the collaboration. Yeah, so that is the second thing. Yeah, that's what is from my side. And similarly, the
Sir,
SDP student development problem. Yeah, hello. Yes,
sir,
sir.
can I please talk, sir?
Yeah, sure. Yeah,
Yes, sir. Myself, Hussein Sheikh, VJT, Hyderabad.
yeah. Hi, Hussein.
Sir, yes, sir. Sir, I couldn't give you feedback, which I wanted to very badly, actually.
Uh-huh.
Actually,
Uh-huh.
sir, I expected a principal and a vice principal to be there in this particular feedback session,
It
actually.
doesn't matter. It doesn't matter. It doesn't matter. Yeah,
No, sir, no, sir.
yeah.
I don't know whether they are going to listen the recording session of this
No,
feedback
no,
afterwards or
no.
not.
That's nobody
Last
will
time also
listen.
it
Yeah,
didn't
that's just.
happen. They have
Uh-huh.
to, sir. They have to see. The real feedback is through this oral feedback only, sir. I
Mm-hmm.
think you will take the initial, the prerequisites, how to make them listen to this feedback, actually. Yeah. So, sir, as rightly said by Principal Garu and Vice Principal Garu, you can see, sir. You see, sir, the number is still 95. I would say that this
Yeah.
95 is the genuine number, sir. This is a
Yes.
genuine number. Each and every participant wants to learn something or the other. Unlike the other FTPs or webinars, rightly said by Vice Principal Garu and Principal Garu. And that is one thing, sir. The second thing I wanted to share with you, sir. Actually, I'm sorry, sir, from all we people that we couldn't make it to some extra hours, so that we can do what we could do in the FTP 1.0. Yeah, yes,
Mm-hmm.
sir. We did write the same thing in the survey that around 6:30 would be good for us. But you remember, sir, we spent 4 hours during FTP 1.0 each session,
Yeah,
isn't
I
it, sir?
remember 4.5. Yeah, 4 to 5 hours.
4 hours.
Yeah.
Only the session is 4 hours, sir, and afterwards we use it to work in the evening also. So entire day.
Hand.
So I told you that that is equivalent to 15 FTPs, sir.
Yes.
So
Yeah.
yes, sir. Sorry from our side only, sir. I think from
No,
next
that's
time
okay.
Next time, I think it
No,
is
no,
not going to
everybody.
be
No, no.
happening.
We have to consider everybody's their own restrictions. Yeah.
Yes,
So that's
yes,
why
yes,
I
sir, yes,
limited
sir.
myself to the complete thing.
Yes, sir, yes, sir.
And in fact, I want to deliver the complete lecture for 2.5 hours and then the assignments. So some of you have suggested that assignments let them do at their home, but most of them has told that they don't have the time because of their family or because of other commitments. So they want to do the
Yes,
assignment
sir, yes,
here
sir.
itself to get clarified itself. So that is the reason I gave the enough time. First I gave some 15-20 minutes, then they told this time is not enough. We couldn't be able to cope up with the next topic. So that is the reason.
Yes, sir, yes, sir, yes,
This
sir.
is not generally I go with the majority. It might be, it
Yes,
is
sir,
a
yes,
kind
sir,
of
yes, sir.
trade-off. I generally gone with the majority, so I gave more time. So, but some of the participants didn't like that way. I mean, they want the complete 2.5 hours to be taught. So, but so
Yes,
if
sir,
you
yes,
might
sir.
have remember in the FDP 1.0, complete 4 hours just I was talking, and then the hands-on was there. So slowly, based upon the requirement from the participants, I try to change the philosophy of teaching, the way of teaching, and the pedagogy in such a way that it will be, helpful for most of the majority. Yeah,
Yes,
yeah,
sir.
because some of them
Yes,
are
sir.
working, some of them,
I know, sir.
yeah. So that is the,
After first day,
yeah,
you might
yeah,
have come to know some different things
yes,
that how it is going
yeah,
to be
yeah, yeah.
designed and all those things. Sir. One suggestion, sir.
That's why,
One only
yeah,
last suggestion.
please, yeah,
Sir, I told this one at the end of 1.0 also. So for example, sir,
yeah,
if it
yeah,
is if you're planning for 6 days, if 3 hours
yeah,
or 3.5 hours is not possible a day, you can extend that one
yeah.
to 7-day FTP, sir. What would you say,
Mm-hmm.
sir?
Yeah, sorry, so to
I
7
mean,
days.
yes, sir. Yeah, rather 6 days. 2.5 hours
Yeah,
is a
it is
day.
actually
But
it is actually the 7 days itself because pre-FDP was 3 hours. I mean, if you
yeah,
see this, yeah, so
yes, sir.
it was already 7. But people, I don't know whether people will appreciate for very long. Yeah, even I can conduct for 2 weeks as well. I didn't have any problem. But uh,
Yes, sir. Of
I don't
course,
know whether
we have to
people
take.
will.
Yes, sir.
Yeah,
Yes, sir.
yes, yes,
Sir, one last thing, sir. I have decided to
yeah.
attend all of your programs, whatever you are going to conduct. In fact, I would like to
Thank you,
meet
sir.
you in person.
Yeah, yeah, sure,
Yes,
sure,
sir.
sure. Whenever if you are
Thank you.
here or I am at Hyderabad, then we will meet.
Yes, sir.
So no problem.
Thank you
At
very
where
much,
you
sir.
are located?
Hyderabad, sir. Hyderabad.
Yeah, in where? Which area?
It is near Langaru, sir. Medipatnam.
Okay, okay, sure. Medipatnam. Yeah. Okay, okay. Thank you. If I am around, I generally come to Medipatnam regularly. If I come, then I will meet you there. Otherwise,
Yes,
you
sir.
can
Thank you very
always
much, sir.
welcome to come to Rajam to meet me. Yeah. Thank you. Thank
Definitely,
you.
sir. If I come there, yes. Thank you very much, sir.
Bye.
Thank you. Thank you.
Yeah. Thank you. Okay, guys. So thank you very much. So what we will do now here is it is 8:45. So I will now activate the link, and this link will be live exactly. The queues link will be active for another half an hour, 30 minutes. Yeah. So please try to complete it one. Just give you the flavor of that one. So it has. So why I have not given you the solution is the reason is that it has some questions from all Q1, Q2, Q3, Q4, and 5, and I additionally added some around 15 more questions. So enjoy this marathon quiz. Thank you all. Thank you. If anything is there, you can always
Thank you, sir.
communicate over. Signing off. Thank you. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you so much, sir. Thank you.
Thank you, sir.
Thank you very much, sir.
Thank you, sir.
Thank you, sir.
Thank you.